So you're asked to synthesize an aldehyde or ketone. Where do you start? That depends on what you're starting with and what you're looking to accomplish. Let's start with turning an alkyne into an aldehyde or ketone. An alkyne is a molecule that has a carbon-to-carbon triple bond that can undergo hydration to give us an enol, which is not isolated, and immediately tautomerizes to a carbonyl. If I react an alkyne with HgSO4 in H2SO4, one of the pi bonds will break. My intermediate still has one pi bond, and where the other one broke, I now have an alcohol. Because oxymercuration follows Markovnikov's rule, if I start with an asymmetrical alkyne, the alcohol will add to the more substituted carbon. This is an unstable molecule, and so the reaction does not stop here. This carbon has both an alkene and an alcohol called an enol, which is not stable, and so it'll automatically undergo an isomerization reaction, specifically a tautomerization reaction called ketoenol tautomerization, which is going to remove the pi bond from carbon to carbon and add it between the carbon and oxygen for a final product with a ketone at the more substituted position. If I take the same starting molecule and react it with B2H6 followed by NaOH and H2O2 for hydroboration, once again the pi bond breaks and I get an alcohol, this time adding to the less substituted anti-Markovnikov position. Once again, I have an unstable enol, that's an alcohol and an alkene on the same carbon, and so this too undergoes ketoenol tautomerization, giving me a primary carbonyl or an aldehyde. So if you're trying to form a carbonyl from an asymmetrical alkyne, use oxymercuration to get a ketone and hydroboration to get the aldehyde. If you're starting with a symmetrical alkyne, it doesn't matter because you'll get the same product. I can turn an alkene into a carbonyl using oxidative cleavage or ozonolysis by reacting it with O3 followed by DMS. Ozonolysis works by breaking not just the pi bond, but also the sigma bond, completely breaking the two sp2 carbons apart and inserting an oxygen onto each of the carbon atoms. I have the mechanism linked below, but the shortcut is simply to redraw your carbon skeleton exactly as you see it, with the pi bonds, but separate them. Add your oxygen in, and you have your carbonyl. So what determines if I get an aldehyde or ketone? You want to look at the number of substituents for your starting alkene. If your sp2 carbon has just one R group and a hydrogen, that will give you an aldehyde. And if your sp2 carbon has two R groups and no hydrogen, the carbonyl formed is a ketone. Only use this in synthesis if you're looking to cleave your carbon chain and have a smaller total number of carbons. Another great way to form an aldehyde or ketone in synthesis is to form an alcohol and oxidize it. Want to practice these reactions? Comment worksheet below and I'll send you a link to the aldehyde and ketone practice worksheet. In general chemistry, you learned that for oxidation, Leo the lion says, "Grrr," which tells us loss of electron oxidation, gain of electron reduction. Electron and proton together make hydrogen. Its loss of a hydrogen is oxidation, and gain of a hydrogen is reduction. Hydrogen and oxygen often add opposite, and so if loss of hydrogen is oxidation, then gain of oxygen is also oxidation. If gain of hydrogen is reduction, then loss of oxygen should also be reduction. That is where we get the alcohol to carbonyl reaction. In this primary alcohol, carbon has one bond to oxygen and two bonds to hydrogen. When I oxidize the primary alcohol, I lose a hydrogen and gain a bond to oxygen, giving me an aldehyde. Why an aldehyde? A primary carbon has a terminal hydrogen. It does not have another R group on the side, giving me the terminal carbonyl, which is an aldehyde. But with a secondary alcohol, my carbon has the one bond to oxygen and one bond to hydrogen. When oxidized, carbon will lose the bond to hydrogen and gain another bond to oxygen, giving me a ketone. Why a ketone? Because the carbonyl has an R group on either side. If a primary alcohol is oxidized to an aldehyde and a secondary alcohol is oxidized to a ketone, what happens if I oxidize a tertiary alcohol? I get no reaction. Why? Because this carbon has three bonds to carbon and one to oxygen. If I try to form a carbonyl to this oxygen, what am I going to lose? I can't lose one of the carbon bonds, and so oxidation would give me 5 bonds to carbon, violating the octet rule and therefore not happening. I want to be careful with the reagents I use for oxidation, specifically in going from a primary alcohol to an aldehyde. Because if I'm not careful, a strong oxidizing agent will take the primary alcohol all the way to a carboxylic acid, which is not what we're looking for. So we'll stick to something weaker like PCC, pyridinium chlorochromate. A way to remember this is that PCC starts with a P. It's a prude and it doesn't go all the way, so it stops at the aldehyde. For a secondary alcohol, you can use any strong oxidizing reagent because it'll stop at the ketone regardless. Strong oxidizing reagents tend to have chromium, such as Na2Cr2O7. You can also use KMnO4. If you're asked to synthesize a ketone from a benzene ring or an aromatic compound, the reaction to know is Friedel-Crafts acylation. This is a simple reaction where you take whatever R group with a carbonyl that you want to add onto your benzene ring, attach a chlorine to it, and put it into a catalyst like AlCl3. Now that you know how to form the aldehyde and ketone, how do you react them? That's what I cover in my other videos, which you can find here or on my website at leahforsyth.com/aldehyde ketone.